Hi, today we are doing the pages in your packet that are labeled More with Transformations. And in this lesson, you will see that one of the reasons that we want to learn about transformations as compared to just being able to graph things on our graphing calculator is that sometimes the parent function is something very strange, such as the graph we have here. So this is what I would call a doodle graph. It's just like a little doodle. And an important part of figuring out what to do with this doodle graph is to identify its key points. Two of the key points are going to be endpoints. So if the doodle has endpoints, you definitely want to identify those. And then the other key points are going to be any turns or corners that you see. And this one has 3. So we'll identify the ordered pairs that go with these. Please label these in your notes as well. Okay, so those are my key points. Now, what I'm going to do is look ahead and see that I have 3 different transformations to do. I have this one, and then I have another couple questions down here. Each of these is a transformation of this same parent graph, this dark blue parent graph that I have. I have 3 children that come from that. Question 1, the only extra bit of information besides just f of x, which is the parent, is that 2. And this 2 is not with the x. A 2 that was with the x would look like this. Okay, and that is not what we have right now. So the 2 is not with the x, which means it's going to be something that influences the y. It is multiplied, and that means I have a stretch. So each point in the parent function, the x is going to stay the same because, see, there was nothing with the x to change that. It's just still x. And the 2 that's multiplied is going to multiply by the y. So this is going to make everything twice as tall. Now, we could go through each of these ordered pairs, like -7, 5, and think about, okay, the x is going to stay the same, and the y is going to get multiplied by 2. And I think that's a really good way to do it. We don't necessarily have to write it all, but we definitely want to do that kind of thinking. Okay, so this first point here is what the green point -7, 5 corresponds to. It's -7, 10 now. Let's do the other green point. The other green point was 6, 0. The x stays the same, and if I multiply 0 by 2, I still have 0. So that point actually doesn't move, and that's because it's on the axis. All the stretching is coming from the axis. So the points above the x-axis are going to stretch up. The points below the x-axis are going to stretch down. And the points on the x-axis are going to stay where they are. With that in mind, I already know where -2, 0 is going to be. -2, 0 is going to stay on the axis, because that's what happens with the stretch. 1, 3, however, is going to move. The y has to become, as we can see up here, twice as tall. So that 3 is going to become a 6. So I have a point at 1, 6. And then I have the last point, which is 4, -6. That would become 4, -12. And then we connect the points from left to right. And this is my new shape. It looks a lot like its parent graph. It is just stretched out to be taller. Okay, this next one is similar in that it is a stretch. It has that 3, but it also has a negative. So this means that every point on my parent function is going to have the y coordinate get multiplied by -3. That's going to generate not only a stretch, but also a flip. So things are going to be flipped upside down and stretched out. Let's take some of these points and just plug them through, okay? So all the x's are going to stay the same. Let's just do these 3 points as a start. And then we're going to take our y coordinates and multiply by -3. So 5 times -3 is -15. 0 times -3 is still 0. Oh, that's right. The things on the axis are going to stay, right? Still the same deal. 1, 3 is going to be 1, -9. We could take that other point that isn't on an axis, on the x-axis, and say, well, that's going to be 4, -6 times -3 will actually be +18, Okay, so let's see what we can do here. Our 2 points on the axis are going to stay where they were. And then these other points I need to plot. So 418, ooh, a little bit off the grid. Thought I'd left myself enough room, but apparently I didn't think about that quite right. 1, -9. And -7, -15. And then there has to be one that I forgot to do. What did I forget to do? Oh no, there it is. Okay, I've got everything, I think. Okay, so this shape is going to come in like this, and then come down like this, and then go slightly off the grid, and then come back down here to the 6. So that does look like the parent graph, but it's flipped over, right? Like this low valley, that's this high point here, right? And so everything's just been flipped over. The last transformation is our good old friend just sliding, okay? So, phew, at least we're done with those stretches. X minus 5, if I were to write this as a mapping rule, I know that X minus 5 on the inside means moving to the right. And in mapping notation, that's how I'd say moving to the right. And the +3 means I'm moving up. And that's how I'm going to say moving up. So I'm going to find all of the points that go with that, okay? Another way I could do this would be to just locate the locations of the parent function points, like -7, 5 is right here. And then I could just count boxes. 1, 2, 3, 4, 5 to the right, and 1, 2, 3 up. I just lost my spot. 5, 1, 2, 3 up there. And that would be my new spot, okay? So I could just locate the points of the parent graph, like -2, 0, here, that little black dot that I just made, and then count 5 over, up 1, 2, 3 squares, and there's a new point, right? So I could certainly keep doing that, and I would locate everything in the graph. So either do plug and chug math through all the coordinates that you have, adding 5 and adding a 3, or find the old points and then count boxes to figure out where the new ones are. But in any case, you should end up in the end with this picture. If you need to pause the video to finish the picture, please do so. Okay, now on the next page, we have a different parent graph. This parent graph is, it's similar in that it is also a doodle graph, and we want to identify the key points. So the key points look to be at -10, -7, -6, +7, -3, 3. This one looks like it's at 0, 6, it's on the axis, and this is at 6, 0 on the other axis. Okay, so those are our key points. Maybe I'll make a little list right here, that might be nice. And then we're going to figure out where those points end up with the different transformations. Okay, so those are the ones on the parent graph. Let's look at what problems we have. Okay, in problem 1, we're moving 4 to the right, up 3, and there's a flip. So the way that we would write that if we were writing a mapping rule is to say, well, the only thing that happens horizontally is the 4 to the right, but we have to reflect in the other direction and also go up 3. So that would be a rule I could use for number 1. For number 2, the only thing that's different is this 1/2. And so every point would just be changed to be half as tall, which means all of the points are going to be squished in towards the x-axis to be not as high up or not as low down from the x-axis. And then this one has a flip. It moves left 3 and it moves up 4. So my transformation rule here would be this one. Negative, that's supposed to, maybe that's a little unclear to see. Let me try writing that again. Negative y plus 4 is what I was trying to say. Okay, so those are the rules that each of these equations suggests. I would like you to pause this video, make all 3 pictures, use a pencil in case you have a mistake, but make all 3 pictures and then come back and see how you did, okay? We'll compare answers in just a minute. You need to pause the video, not just listen to me show answers, okay?